Hey there everyone, I hope you guys are doing well. Today we are going to talk about the electromagnetic radiation. And what is the electromagnetic radiation? And basically we are going to try to look at the electromagnetic spectrum as a whole and try to look at each zone of the electromagnetic spectrum and explain what it does and its applications maybe, and where it's coming from, where it goes and stuff like that, okay? So if we look here, this is the electromagnetic spectrum, and I took this picture from Wikipedia. Thank you very much, Wikipedia. So in this here, we have, this is the wave that represents the wave. If that was representing the wave, that's how it should look like, of the electromagnetic radiation. Then we start from the smallest wave to the biggest wave, okay? And this is actually a physical length, okay? So what is the electromagnetic radiation? Electromagnetic radiation is all the lights you see around. This is the light here that we have, is just the visible light as part of the electromagnetic radiation. You're using X-ray to go and take some images of your bones or inside your body. Both X-rays and microwaves you cannot see, which is lucky for us because imagine you have to see all this other electromagnetic radiation other than the visible light. There will be a lot of noise, and we will talk about that more. So let's start with the gamma ray. Gamma ray is the most powerful electromagnetic radiation, and the size of the wavelength is 10 to minus 12 meters. So this is 10 to minus 12 meters. So it's really, really small, okay? The size of basically a nuclei of an atom. Alright, so who can see this light? If you were the size of a nuclei of atom, you would be able to see gamma ray. The power of, or the energy that they carry with them is so huge, they can go through almost anything. They can go through concrete walls, they can go through cars, they can go through air, they can go through whatever you need. So they are very powerful and, of course, destructive too. You know, you don't want gamma ray to go through your body because that will hurt your body a lot. Just like X-ray. X-ray is less powerful but still high energy electromagnetic radiation. It is the size of an atom, and as you know, atom is a little bit bigger than the nucleus itself. This is the nucleus. Okay? So the atom is almost like 100,000 times on the average more bigger than the nucleus itself. Given the numbers here, it's 10 to minus 10 meters, okay? So if you were an atom, you would be able to see this X-ray radiation. And the X-ray radiation is also very powerful. You know that because it goes through your body. That's how they can take an image of your broken hand or a dislocation of your shoulder or something like that. Another powerful and high energetic radiation is the UV or ultraviolet. However, the energy of this, as you can see, is less. UV comes from the sun rays. So if you sit under the sun for a long period of time, like more than 1 hour, you will see that your skin color has become a little bit darker. And the reason for that is that the UV comes and your body absorbs that UV, and chemical reactions in your skin take place, and that's why the skin color changes. UV also, you don't want to be exposed to UV for a very long time. You know, you hear about a lot of skin cancer. They could cause skin cancer for prolonged time exposures. Okay, so UV also now it's used for killing the coronavirus in airplanes. For the recycling system, where air is taken into these recyclers inside the airplane. It goes through UV light with some certain mechanism, and it kills all the germs, including the coronavirus. And if you are probably a biology major, you will know that UV is also used to clean dishes before they go into culture, so that they make sure that there is no excess bacteria or whatever, or harmful things that could change the course of your experiment. All right. Another thing we want to talk about is the visible light, and you know this. That's where you live. Anything you see is visible. And the thing about visible light, it's a very, very narrow part of the spectrum. Very narrow part. Okay, look how big the spectrum here and how big the spectrum here. We can only see within the visible light, and it's a very narrow part of the spectrum. And that's good, as I said, because you don't want to see the X-ray, you don't want to see the gamma ray. There's a lot of noise here and there. So you want to, that's good that you're only able to see the visible light. All right, now after that, the infrared light. If you sit under the sun and you feel warm, that's what gets you warm, the infrared light. Not the visible light, not the UV, not anything else, but what? The infrared. And there's many applications for that, like what? Like the infrared binoculars, where you can see objects at night, and the way you see it, it's just because they are, they have their heat signature. So if a hot body looks like a little bit red, a colder body looks like a little bit bluish or whatever, so they can see objects at night if they are radiating heat or not. And it's used also in houses. If somebody working in construction, they want to see where the house is leaking energy, they go outside and they take footage of the house, and they can see, for example, okay, under that roof there is a heat signature coming out. This means that probably air is escaping from that area in the cold weather. Now comes what? The microwave. And you heard about the microwave a lot. That's what your phone uses. And the microwave is the same as the microwave in your appliance in the kitchen. And it heats up food. And the way it heats up food is just because microwave goes up and down, up and down. And it coincides with the normal frequency of the water molecule. And it flips the water molecule up and down, and every type of food has water molecules, including water and milk and everything. Microwave starts flipping the water molecule up and down, and this process produces heat, and it heats up the food, and that's how things are heated up. So your microwave waves do not escape outside the microwave, because your microwave is made into something we call Faraday cage. So it prevents the harmful microwaves, the high intense harmful microwave, from escaping out, right? The same argument can be talked about your phone. So if you're using your phone a lot, once 20 or 25 years ago, when the cell phones started, there was a lot of discussion if they heat up your brain, and if they are causing your brain to change in a way. No merit was found so far, and because it's not high intense microwaves. Now, as we move from right to left, as you can see, the wavelength increases, and as the wavelength increases, the energy goes down, and the biggest waves that we know in size are the radio waves. I mean, the size of this could be 1 kilometer long. This is huge. Let's look at this again. So as we move from right to left, as you can see, the wavelength is increasing. So lambda here is increasing, and lambda here is what? Decreasing. Something else we noticed, we were talking about energy. Gamma ray, we said it has the highest energy, while here energy is the lowest. So it seems that as the wavelength increases, energy goes down. And they said, okay, look, the frequency here is high because the amount of oscillations happening in a certain time is high. Here the frequency is low because the amount of oscillations happening is low for a certain time. So that leads to that the frequency and the wavelength are opposite to each other. When we have high frequency, we have what? Low wavelength. So I'm going to say here, frequency is high and wavelength is low. And here, as you can see, the frequency is low. Okay? What do we learn from that? We learn that the energy is proportional to the frequency. If the frequency goes up, it seems that the energy also goes up. And we also learned that the frequency times lambda the frequency times lambda, because one of them goes up, the other one goes down, and they interchange linearly. So if lambda goes up by 2, the frequency goes down by 2. So they do that linearly. So it was found that the frequency times lambda is equal to a constant. So that's always a constant. And not only that, the frequency times lambda, this constant was found to be the infamous speed of light. And the speed of light, I'm going to put that down here. Lambda times the frequency, or frequency times lambda, is equal to c. The speed of light is equal to 3 times 10 to the power 8 meters per second. Can you imagine how fast the light is? It's 300,000, no, not 300,000, 300,000 kilometers per second. Multiplied by this, 1,000, so 300,000 times 1,000 is, so it's 300 million meters a second. That's a huge speed, So the light can go around the Earth, like, I think the Earth is about 40 or 45,000 kilometers in circumference. So light can go around Earth in less than, it can go around the Earth 5 times in a second, or even much less. So it's amazing. So the speed of light is huge, and I want you to recognize this very well. So now I'm going to write this equation again. The frequency times lambda is equal to 3 times 10 to the power 8 meters per second. And that's a very important equation. I would like you to memorize it or make sure that you know it. Okay? Alright, now let's look deeply or more in detail into the speed of light. So this is, we said it's a huge speed, as you can see. Nothing can go that fast. It's the absolute speed in the universe. Nothing can go faster than the speed of light. Even light itself cannot go faster than the speed of light. You may ask, well, how is that possible? I'll tell you. If there's a vehicle that is traveling at 100,000 meters per second and it shines out a light in the same direction, you would think, oh, so this vehicle is 100,000 meters per second and light is 300 million. Add these together so that light will be added together because they're both traveling at the same direction. But that doesn't happen. Light adjusts itself so that it does not exceed its own speed. Isn't this amazing? It's amazing, right? Light is the only thing that does that. So we know the speed of light is huge, but now let's look here. We are here at Earth, okay? Oh, sorry, this is Earth, I mean. No. This is Earth, okay? And there's the moon here. The moon is a little bit shy of 245,000 kilometers or something like this. So if somebody on the moon shines a laser, it gets to Earth in less than 1 second. That's how fast the speed of light is. So less than 1 second. It takes light to travel from the moon to Earth. Now let's go to the sun. And if somebody on Earth shines a laser on the sun, or let's say somebody who lives on the sun shines a laser back on Earth, it takes about 8 minutes for the laser to get to Earth. Okay, so here's a quiz for you. If somebody comes and switches the light on the sun off, when do we feel it as Earth people? We feel it after 8 minutes. We will get cold after 8 minutes. So it takes 8 minutes to know, all right? Now, this is the sun, and as you know, the sun is a star. The nearest star after the sun to us is called Alpha Centauri, and Alpha Centauri is about 4 light years away. Look, moon is what? Less than a second away. The sun is about 8 minutes away. Alpha Centauri, which is the closest star other than the sun to us, is 4 years away. And so if somebody shines a laser here, it gets to Alpha Centauri, or somebody who lives at Alpha Centauri 4 years later. So basically, let's say you have a friend who lives at in Alpha Centauri. And you have your phone and you text him and you say, hello. It takes 4 years to get the message. So they say, hey, hello, how are you doing? So it gets you an extra 4 years to get the message. So before you receive a reply, it will be 8 years. Can you imagine? And that's the closest star to us in our galaxy. So since it's taken 4 years, they called it the light year. Why light? Because that's the speed of light. Now, we are living in a galaxy known as the Milky Way. Earth is somewhere around. The distance between, or the diameter of our galaxy, the Milky Way, is 100,000 years. 100,000 light years, that is. So if somebody shines a light from here to here, it takes 100,000 times. So basically, if you are here and you are looking at a star, and you can see a star at the end of the galaxy, because some stars are huge, and this star has exploded 90,000 years ago, you wouldn't know that it exploded, that you wouldn't know that it does not exist anymore. Okay, and the reason is the information from that explosion has not arrived to us yet. So you think everybody is living there happy, but they've been gone for 90,000 years. Okay. Now this is the Milky Way. There is other galaxies. Each galaxy has their own stars. It's crazy. So the galaxies are sailing across the universe in the universe, right? So how big is the universe, you think? So if there's the edge of the universe here to here, just a few years ago, many years ago, we knew that it was 12 billion light years. Can you believe that? 12 billion light years. So if somebody shines a light from here, it takes 12 billion years to get to the other side. However, we were wrong. Just a couple of years ago, there is a new discovery that puts an estimate on how large the universe is, and they think it is 78 billion light years big. Can you imagine how much of a mind-blowing this is? Where are we? This is our galaxy, part of hundreds of thousands of millions of billions of galaxies in the universe. And each galaxy has stars in it. Stars, like our sun, bigger or smaller. Stars, more than there are sand. Each galaxy has more stars than what we have as sand dust on Earth. Can you believe that? So hundreds of billions of thousands of galaxies, hundreds of billions of thousands of stars, right? And there we are, just a small dot in an expanding, huge universe. That's it, everyone. Thank you very much.